Right, so let's get started. So there's been a Christmas break, winter break, nice. And now the grading for the exercise 2 is ready. There'll be a tutorial after the lecture today, okay? And Elisa will be giving the tutorial. And now the final exercise 3 is available on the web, the course webpage. So you can take a look. And Michael will be in charge of this exercise. And yes, I think I'm recording now. Good. Yep. So let's get started with the final, probably not the final part, because there is one little single lecture at the end that I wish to kind of keep for the last topic. But yeah, the topic for today and for the next 2 lectures is uncertainty estimation for neural networks, for deep neural networks. So let's motivate the story with some meeting that I had with another business. Right, I was working at a company, and then it's kind of typical that teams that do not really know machine learning, they tend to kind of downplay the hardness of doing something. And typical subject that comes out is why isn't it so trivial to just make your system predict confidence? Right, because we really need it. And can you just do it, right? Why can't you do it? And it turns out that since I get a lot of such requests, it turns out uncertainty estimate is a very important building block for many systems, especially if there are many modules in the pipeline. And the module that you wish to plug in is kind of a machine learning-based, data-driven module. And of course, if there is any data-driven kind of component there, it's not easy to trust everything from coming out of this module, okay? So to take care of the possible imperfection of that module, what people do is basically not trust everything that's coming out of this module. So for example, they can have later on human in the loop. And when the model says, for example, I'm not too sure about the result, then human comes in and make a fix of the output. Or if the model says I'm not sure, then what happens is everything stops and determines that this is a very risky situation, and we should probably not take care of this input anymore and just stop. Okay, so instead of having just prediction results, once you have those associated uncertainty of your module, then you have a lot more choice of what to do next, what to do after this module. Okay, and that's useful in many cases. For example, there are some products for image search. I mean, Google image search is also out there, has been there for a long time. But usually the search is, I mean, for those companies, they are really motivated to link the image search result to actual products to make money, right? And and of course, these customers are also interested in those kind of applications. But let's say a customer does not take any product inside an image and still wants to search for whatever product that's supposed to be contained in the image. Then what the system could do is to determine if there is any object in the image and say, when there's no interesting object, say that the user should be probably posing the camera in a different way or try to focus on the object of interest, and so on. So there can be some kind of feedback loop here to make sure that the model can perform in the right way. And of course, if you go on to more and more serious applications like healthcare, determining if there's anything wrong with your body or not, okay, then having access to this kind of confidence matters a lot. So now the model has some kind of confidence prediction, and you put some kind of threshold on top of that. And you only trust the model when there is confident prediction, which is beyond certain threshold. And whenever the confidence is lower, then you just ask the human doctor to come in and take a look. One way to think about this is when there is a high stake in, oh, what's happening here? Okay, I hope it's still recording and everything is good. Okay, so I think the screen share has been interrupted. Right, this is the right one. And I hope the recording is still there. Yes. So yeah, anyways, if there is high stake in wrong, this is false negative, right, for the disease diagnosis, then there is a huge cost, 10, right? And you do not lose a lot of cost by saying, I don't know. So when you're very sure, then you say, yeah, I found the disease, or I didn't find any disease. And if you're not sure, then you'd better just consult the doctor. Okay. Yeah, it's a pair that comes up together in many cases: self-driving cars and healthcare. So self-driving cars, you do not wish to really let the current self-driving systems to drive in any case, right? Like if there's no light in your sort of highway, then you wish to kind of make sure that it doesn't crash into the wall or outside of the road, or if it's a very busy city situation, then you wish to kind of take over the control. In very heavy rain or snow or thunderstorm, you wish to kind of take responsibility of your driving. Okay. This is kind of a different type of scenario where this is more specific to the classification task. When you do classification, you first predefine a set of classes. For skin conditions, for example, you define like, I don't know, 100 popular skin condition classes. But of course, if you deploy this kind of model in the real world, there can be very rare diseases for your skin condition. And you do not want your model to say, yeah, this is still normal, or say, well, it doesn't look as normal, but since I need to pick anything among the known cases, I would say, yeah, maybe this is just acne. That's not good, right? So a classification system should also probably be able to say, yeah, this is something that I have not learned before. This is a new class, right? The same goes for the cases where you have, it's kind of a growing field, right? So for example, you know more and more bacterial classes in biology. I don't know much about this, but if you have more and more kind of entries coming into your database of bacteria, then you wish to kind of be prepared for new bacteria classes in the future. And yeah, but of course, if you train a classifier, you can only train on the classes that are in the database. And for the future cases, you wish to kind of assign, I don't know, label to them, right? And they can be used later on for further training the model, or yeah, or you can put labels on them and then, yeah, further train the model. Yeah, that's what I wanted to say. And that brings us to active learning as well. if you know active learning, it's basically finding samples to label. So instead of just having a huge set of unlabeled samples and then going through this whole set to label everything, you pick the samples that the model is very likely to be confused, and then asking for human feedback for those samples. And by doing this, we are maximizing the utility of humans, which are typically expensive. Okay, and for telling which one of the unlabeled samples is most likely to return the highest return when they are annotated by human, we should rely on some notion of uncertainty and confidence values. Okay. And what is also highly related is, this is actually not active learning, it's a wrong kind of heading, but for hyperparameter optimization or any kind of Bayesian optimization and experimental design, what is important here is that you need to tell, you're basically searching through a huge space, combinatorial space of possibilities. For example, let's say you're doing a hyperparameter search for training your model. Okay, then you have learning rate and the number of layers, the width of the network, weight decay, whether to do augmentations, the number of epochs, the learning rate scheduling, the type of optimizer, and so on, right? And if you multiply all choices together, then that's going to be like thousands and millions of possibilities. And by using Bayesian optimization, you can kind of, in a sense, you're reducing uncertainty for in this complex landscape. So by observing a few data points in a smart way, that's most likely to reduce your uncertainty. And by updating your belief based on the results of training models based on those very well selected hyperparameter configurations, you're reducing your uncertainty over time, and eventually you'll find the configuration that's very likely to maximize your return. Okay, and here, of course, you need to explore the space in the most efficient way, and there you need to have some notion of uncertainty. And back to more kind of simpler case, in a sense. You have object detection pipeline here, and yeah, object detection also contains multiple modules in its construct. So for example, this RCNN is an old object detection pipeline, and this also has multiple stages. And the first stage is it's called proposals, box proposals. So given an image, it proposes like thousands to millions of bounding boxes inside the image that is likely to contain any kind of object, okay? And they come with confidence scores. And therefore, you can threshold according to the confidence score, and that's going to return you the most likely boxes containing any kind of object, okay? And on top of those boxes, you are running a classification, image classifier on top. So now with the box, you run the classification and you're going to have the object class label. And that's exactly what you need for object detection, box and the class label. So that's another example. Whenever you have multiple modules here, you will very much likely to require any kind of confidence score. But also to be more kind of, how to say, more general, I would say confidence estimation is needed in general when the outputs cannot be treated equally. Some of them are probably less trustful. And one thing to keep in mind is that confidence estimation is probably not needed when the system is always perfect. Then, yeah, why do you need confidence estimation? So eventually, when such a time comes when AI systems are always making the right answers, then this study is useless. But we'll see if that happens. The other important topic to cover here is what are the possible causes of uncertainty? How can one say, in what kind of situation can one say, I don't know, or I'm not sure? So I'd like to identify two typical cases which are important in machine learning context. So the first one is, I don't know, I'm not sure, because I haven't seen it before. I have no experience. This is called epistemic uncertainty. And the second type of uncertainty is yeah, I have experienced it before, but I know what I'm doing, but still, I think there are more than one good answer to your question. And so I can't say, if you tell me I should choose one good answer, then I don't know. I don't know what to say. That's called aleatory uncertainty. Okay. So let's go through each item. So let's talk about epistemic uncertainty first. So this means the uncertainty comes from the lack of experience. And this has a close connection with Bayesian perspective learning. Okay, what is Bayesian perspective learning? You start from some kind of prior, and then you accumulate observations. And then afterwards, you have some, you can make some prediction based on your experience through observations. In other words, you have prior, and then you have likelihood, like stack of likelihood for each data point. And then as a result of that, you have posterior. In equations, you have posterior, which is proportional to the prior times likelihood, where the likelihood is just the product of all the individual data sample likelihood. Okay. So what uncertainty here means is when you don't have any experience, right? Then you're in the stage of just having prior, right? And by just having prior, yeah, you have many possibilities for your theta. And typically your entropy for theta decreases with multiple observations, okay? So that's how you reduce your epistemic uncertainty. You're kind of reducing the search space for your, or the possible space of like list of models that satisfy your data, okay? So this is another way to see that, right? So let's say you have training data that looks like this for binary classification. And typically there are not a single model that fits the training data well in your huge class of models. For DNNs, the class of models is huge, right? So the number of possible models that satisfy the solution is huge. And we say the model uncertainty is reducible. What does that mean? That means if you have infinite data sampled, then you can actually rule out certain models. Okay, that's probably more clear in the next slide, actually. Because you see that those areas are underexplored, and by collecting data samples from those areas, we can actually determine which one of these models are doing the good job, okay? But here the caveat is that actually this statement is a bit imprecise, because if your data distribution is not covering certain areas, then you still have uncertainties there, right? So what is important is to explore regions that are underrepresented in the original training data, okay? These are OOD samples. So as soon as you collect a lot of OOD samples and label them, then you can reduce epistemic uncertainty as much as you like. Yes?
Sorry, I just want to make sure I understood the. In other words, the model is unable to say how confident this was certain prediction, like how far a certain sample is from the boundary, because it's not sure where the optimal boundary should lie, because there are unexplored space within.
Sorry, I didn't get the question. Sorry.
So is it correct to say that epistemic uncertainty means the model is for a certain sample uncertain about its confidence level because like it doesn't have information about where exactly the boundary lies because there are like unexplored spaces.
Yeah. So I'm kind of seeing the boundary and model, the decision boundary and the model kind of equivalently.
Yeah.
So I'm kind of seeing those lines here as decision boundaries as well as models. Okay, so as soon as you sample a few more points here, I think as long as there's no label noise or ambiguity, you should be able to pin down which one of these three is the most likely solution. I think that's what I mean. Okay. And active learning is, of course, linked to this observation, right? So you can use the epistemic uncertainty to sample from the regions where the model needs the most samples, okay? And yeah, it takes place when distribution shift takes place, or there's a novel concept as well, okay? And then now moving on to aleatoric uncertainty. It means I don't know because there are multiple possible nice answers, plausible answers. Let's consider a predictive task of predicting y from x. Aleatoric uncertainty takes place when the true distribution of p of y given x is multimodal. Or yeah, it doesn't actually even have to be multimodal. It just has to be non-deterministic. It should have some kind of variance. Then we say there's aleatoric uncertainty. But the most extreme case is when you have multimodality of the outputs, okay, possible outputs. What is a good example of that? Actually, good examples are everywhere in machine learning as well. This is simple CIFAR, I believe. Yeah, it looks like CIFAR. And these are human agreements, okay? So you're giving this sample to 10 humans and asking them what the label is, okay? And for these two samples, it turns out that it's fairly obvious that the first one is plain and the second one is cat. However, for those samples, yeah, people disagree quite a bit. It looks a bit like cat, but also, yeah, this could look like sheep. Yeah, I don't know. Yeah, I'm probably one of those people. And the second one, it looks like deer, but also a bit like cat and maybe bird as well. Yeah, so the point is that even for humans, for this simple CIFAR data set, the true y given x could be multimodal, where the true here means true for human. Yeah. And the other example is when you have ambiguity in the question, okay? So this is an example of ImageNet. The label for this image is desk, and you know that there are 1,000 classes in ImageNet. So it's very likely that another category of the 999 categories will be present here, okay? It turns out that there's screen, there's monitor, and coffee mug that are part of the 1,000 classes of ImageNet that are also present here. But you know, ImageNet annotators are only required to provide a single label per image. And so the true label for this image is just desk. And if you train with this kind of data set, then the model, for the model, it's not a solvable problem because the same image could have just had the other labels as well. And that's not wrong, right? So that's allometric uncertainty. And also, there are cases when the input goes through some kind of occlusion or some corruption, which removes some features. Okay. So for the first image, the upper part of the first digit is gone. And that could have been 17 or 47. So the ground truth P of y given x is maybe 0.5 for 17 and 50% for 47. Okay. So this is another kind of way to visualize how this ambiguity could arise, right? So for example, the features are well separated when you have two features available. Like for example, if you know all the features here, then you know that you know what is 17 and you know what is 47. But as soon as you remove some part of the image, like this x2 is that part of the image, let's say, then suddenly you have overlaps in the features for the first one, right? And yeah, so missing features are also another typical source where you introduce allometric uncertainty. In a sense, these cipher images are also a good example of missing features, because as soon as you take a photo of this airplane, and obviously here it looks like it also went through some kind of extra corruption of reducing the resolution and so on. I think these are even thumbnails or something for some purpose, right? And then you're removing information, and so that introduces uncertainties like these ones. If those objects are actually seen in the real world, then probably there's no ambiguity at all. Okay, but still, whatever the source is, eventually when you have ambiguities and multiple plausible answers, then we call it allometric uncertainty. So even for allometric uncertainty, there could be different sources. Yeah, this is another example. If the task is to tell how many people there are, then it could be 8 people, 9 people, 10 people, and so on. Or the other type of allometric uncertainty is when the task itself accommodates multiple plausible answers. So text-to-image generation is a good example of that, right? So this caption is it's just a nice caption that they seem to promote in DALL-E 2. And if you give this caption to the system, then it generates these images, and all of them make sense for this caption. Crayon drawing of several cute, colorful monsters with ice cream cone bodies. Sorry, monsters with ice cream cone bodies on dark blue paper. Yeah, they all work. So it's kind of it's another kind of extreme of allometric uncertainty. Your answer is not a single one. So we said that epistemic uncertainty could be reduced by introducing more training samples from underexplored regions. But it turns out that for allometric uncertainty, we cannot really reduce the uncertainty by just observing a lot more data, because you're still going to see the multiplicity. Like for example, for this image, you're going to see labels 8 or 9 or 10 multiple times, and by seeing ambiguities multiple times, you do not really reduce ambiguity. In a sense, when you train with this kind of ambiguity in your training data, you're actually introducing mixed supervision. For the same input X, you're going to see multiple different supervision. Okay, because for example, you're going to see this kind of sample, and then sometimes the label for this sample is 17, sometimes the label is 47, like 50-50. The same goes for this one. For the same image, you're going to see label desks, sometimes screen, sometimes monitor, and so on. Of course, in ImageNet, you're not going to see the exact same image with multiple different labels, but you're going to see very similar image like this one, but with different labels. And the model learns to kind of see the similarities between the images. And the model gets confused if it sees the kind of similar images, but with very different labels. Okay, so that's what's going to happen when you have this kind of aleatoric uncertainty in the training samples. Same training samples with different supervision. So how do you address it? It's not easy to address it just with normal solutions. So you have to actually change the model architecture as well, in such a way that the model now accommodates multiple possible plausible outputs. And you also need to adapt a learning strategy that lets the model learn multiple plausible answers rather than sticking to one. If you just train a model, then the model is very likely to stick to one choice. So to make further comparison, I would like to summarize that this is epistemic uncertainty, right? Because the classes kind of overlap here, and the P of y given x is, has variance here. Okay,
that's
sure. Yeah, this is aleatoric uncertainty. Yes, exactly. Did I say epistemic? Okay, yeah, sorry. Right, so this is aleatoric uncertainty with a multiplicity of possible answers. And epistemic uncertainty is also about multiplicity, but now with multiple possible models. So one is more from the data uncertainty, and the other one is a more model uncertainty. Okay. And there's a paper which came up with a system which is capable of representing or measuring epistemic uncertainty and aleatoric uncertainty at the same time. And this is kind of the result that you see from this paper. So given an input image, the task is to predict the semantic segmentation, pixel-wise classes, okay? And here's the ground truth classes, and here's the semantic segmentation. You see that sometimes it's not perfect. For example, here, right? The poll is not predicted correctly. And the system is able to tell which part of the image has the highest aleatoric uncertainty and epistemic uncertainty. So if you look at aleatoric uncertainty, it arises typically in cases where there is a boundary between the classes. For example, between this pedestrian and the actual street, the road, okay? And the guess here is that when people annotate pixel-wise for those kind of images, the mistakes for the labeling takes place usually around the boundaries of the objects of the classes. And because there are mixed supervisions for those boundaries, it leads to higher aleatoric uncertainty eventually. Okay. On the other hand, epistemic uncertainty is not picking up those boundaries, but it's more looking at part of the image where the kind of pedestrian, for example, here is something that it has not seen before. I don't know. I haven't seen all the training samples for this model, so I can't really tell, but probably it means that the pedestrian here is something that's not so typical. I don't know. Yeah. But this is kind of the idea of aleatoric versus epistemic uncertainty. So we're going to talk about addressing those uncertainties in the coming lectures. That's going to be fun. Right, and now we talk about evaluations. How do we define uncertainty and how do we evaluate it? Because without evaluation, we do not progress. So we start with the question of what is the data format exactly for uncertainty or confidence? I kind of use confidence and uncertainty exchangeably. 1 minus 1, 1 minus one of them is the other one. Yeah, okay. So let's say there's a simple model format here. So given an input, it gives an output. But we're going to consider the confidence value to be just a scalar, which is between 0 and 1. If something is a scalar which is between 0 and 1, we can just call it probability as well. Okay, so we're going to treat it as probability. So this is our basic format for confidence value. We can think of more complicated data formats. Instead of just a scalar, C of X, there's a comma missing here. C of X could be just a scalar, or the model can just report an array of scalars. In other words, a vector or a tensor, okay? So a good example of more complicated confidence value is when you have confidence value attached to each attribute for the sample, okay? So let's say the system is a person identifier or person classifier. Let's say this person is ABC, and you can attach a confidence value according to different supporting evidences. So for example, the confidence for the prediction of hair color is 99% because I kind of see it here. But for eye color, which has lower representation in the image, especially in this kind of blurred sample, we are not very sure. And for the mouth shape, we are not even sure what the mouth shape should be like, okay? So just an example of what this could be. You can also report aleatoric uncertainty and epistemic uncertainty separately. So we have seen example before, right? From this paper, right? And they report two different uncertainty values based on these different computations. I'm not going to explain what these are exactly. What is important here is that in this case, the reported uncertainty is not a single number, but actually two numbers. That is also possible. In the more extreme cases where the prediction is not just a number or two numbers or multiple numbers, it can actually even be parameters for a full distribution. Let's say your predicted value from this network is actually a distribution rather than a single point, okay? Then you have mu of theta and sigma of theta, which are the outputs of the network. And you can think of sigma theta as some kind of representation of uncertainty, because that's encoding the variance of your Gaussian. And in this case, you have full D by D matrix for representing this, okay? So that can be more complicated way of saying I'm not certain or I'm certain. So given that this is kind of interlude slides where I wish to make connections to other trustworthy machine learning topics so far. So for example, epistemic uncertainty has a lot of connections with out of distribution generalization talked about in lecture 4. For example, epistemic uncertainty should be high for out of distribution samples, right? And we talked about training only with the diagonal samples and the multiplicity of plausible models that fits to this these diagonal samples, right? And since there are 3 different models that are possible and they do not really agree on the off-diagonal kind of region, we can say that the off-diagonal region has high epistemic uncertainty because the model outputs for those samples are huge, okay? So in other words, epistemic uncertainty is closely linked to the diversity of predictions for different models that are equally good on the training samples, okay? So the variance will be very low for these models on the training samples, but outside of the training samples, the variance will be higher. And the way we measure eventually the epistemic uncertainty is essentially by training multiple models and seeing how much they agree on the sample or not. That's it. And that's actually the essence of Bayesian machine learning as well. You train multiple models at the same time in a more smarter and efficient way, and then check their divergence. And generally, uncertainty also has a lot of connections with explainability, because when a model returns how confident it is about something, then that's a great opportunity for the user to learn more about the model and the output. For example, we can answer questions like how uncertain was the model about the prediction, or due to which factor was the model uncertain. And the other question is, which additional training data is likely to make the model be more confident? And these are all interesting questions for explainability as well. But given all that, we still stick to scalar confidence value for basic evaluation. Okay. Okay, so I'll take 5 minutes break here and then resume in 5 minutes. Yep, let's get started again.
I have a question.
Sure.
The uncertainty is relative to the data, right? So it's a feature that only depends on the data, not on the models.
It also depends on the model, right? Because the model is the one who is uncertain about the input.
So what we want to get is how well the model, the confidence on the model about the data.
Yeah. So it actually it's encoded in the evaluation metric actually. So some evaluation metrics wishes to measure the likelihood of the model failing, whereas some other metrics wishes to measure how out of distribution this sample is. In that case, the uncertainty measure that we wish is probably not dependent on the model itself, right? So there are different versions that we are probably going to touch upon these differences later on. So, yeah.
Thank you. So in one sense, when we reduce the capacity of the model and make it work with an electoral uncertainty, right?
I think no, I think what you mean here is that probably allometric uncertainty does not depend on the model itself, right? I don't think it depends on the model actually, in this case.
So it's independent, but can you do it independent of the tool?
When there's allometric uncertainty, it's independent of the model, I think. But also you can still say you wish to get allometric uncertainty of the model. But I think eventually the right measure of allometric uncertainty, eventually the only correct way to measure that is to look at the data. But it's impossible to measure that without any model, right? So eventually you will have to borrow the power of some data-driven model to measure that. So, yeah. Yeah. I hope it's clear after the second part of the lecture. So a critical component of the trustworthiness of machine learning system is how truthful the confidence estimate is, right? So I'll tell you one, perhaps the most popular demand for the confidence estimate. Let's say it's C of X, okay? And the requirement goes it should quantify the actual probability of the model to get the prediction right, okay? So if the probability of getting the prediction right for this sample X is 50%, then C of X should also be 50%. So we'll talk about how to encourage that behavior in general. And let's think about dealing with people. And the best way to optimize the behavior of a person is to give money, okay? Some kind of reward. And let's say this is a simple forecasting task. And we let them bet on the probability of rain tomorrow. Okay, so if C is higher, then there's larger bet on the rain, and vice versa. And we want the subjects to be truthful to their belief. And the way we encourage this is to give money based on how correct they are. Okay, so S, let me quickly check if I'm recording this. Yes, I'm recording it. So S is telling us how much money we should give them based on their confidence score C and the actual outcome Y, whether it's raining or not. So Y equals 1 means the prediction was correct, and Y equals 0 means the prediction was wrong. And we are assuming that the subjects are rational, meaning that they are always trying to maximize the expected amount of money that they get. So the question here is, how should we design such a reward function S? Okay. And the expected reward can be encoded like this. So there are two possibilities for Y, right? Y could be incorrect prediction or correct prediction. Depending on the actual probability of the correct prediction, you're going to get different US dollars. Okay. And the question here, again, I'm reiterating, is that we should find the right function S of two values here, such that the max value for this expected reward is attained if and only if the confidence is truly representing the actual probability of getting the answer right. Okay. The other way to say this condition is that the reward should be largest. The reward should be always smaller than this case when the C is said to be the actual probability of getting it right. Okay, and here the equality should imply C equals to P probability of Y being correct prediction. Okay. We call this kind of reward function a proper scoring rule. So what is an example of proper scoring rule? It's a log probability, for example. Okay, I'm going to define when there's a confidence value C, I'm going to say you're going to get a reward of log of C when the prediction is right. And you're going to get the reward of 1 minus. It's actually not a reward. It's because this value is always minus, right? So I'm going to take less money from you if you get the prediction right. So that's kind of weird here, but yeah, I didn't want to put minus everywhere and change everything. Right. So I hope the meaning is clear here. Yes.
Just a quick push more notation. So on this equation on the left, the capital Y means prediction, but on the right it means ground truth, right?
No. Actually, Y here means correctness of your prediction. Why did you think Y is the rain or not?
Remember the slide there? I also think that Y is the ground truth, according on the first slide.
On the first slide here. Okay, so here C actually means the probability of rain that it predicts.
Yeah.
Okay. Yeah, that's true. So in this particular example, it doesn't matter whether you consider Y to be the ground truth or the correctness, because C is both the probability of rain the person believes,
Okay.
as well as the confidence for that prediction. Okay. But for multi-class prediction tasks, they are kind of different. And so I wish to stick to the definition of Y being making correct prediction versus not, and C being the confidence value of making the right prediction for this sample. Okay. I will try to fix the slides in a way that it's more clear. But ask me later on if anything is unclear for any of you. So it's basically a binary classification task then, right? Of whether I'm gonna make the prediction correct or not. Okay. So you have the original task of whether telling whether this is going to be raining or not. But the task for C actually is the prediction of whether I'm going to make the prediction right or wrong. Okay, and here the scoring function for that is if you make such a confident wrong prediction, then you're going to get -infinity penalty and vice versa. And here, if you plug in this S of C and Y into the expected reward, then it looks like this. You're going to get log of 1 minus C reward when the actual outcome is Y equals 0 and vice versa. And as an exercise in the final exercise sheet, you're going to show that this is actually a proper scoring rule. Okay, so I'm not going to talk about that here now. But I'm still going to show you an example for the other proper scoring rule, how one could compute this. This is another proper scoring rule, where you take the square between your confidence value and the actual correctness of your output. Okay, and you take minus, right? Because your reward should be higher, closer to 0, when the confidence value and the actual prediction are closer to each other, okay? And the expected reward for the subject in this case is minus C squared when Y is 0, right? Okay, and you have to multiply with the probability of Y being 0. And when Y is equal to 1, then you have 1 minus C squared, okay? And there are minuses everywhere. And for the sake of simplicity, we can write A as the probability of Y being 1. And the probability Y equals to 0 is 1 minus A in that case, right? So we can simplify everything to this equation here. And we're going to show that this is a proper scoring rule. What does proper scoring rule say? This value is maximal when A is equal to C, or C is equal to A, right? That's what we need. And we can actually simplify this equation into minus C squared plus 2AC minus A. And it just boils down to see that the maximal value for this equation is taken at C equals to A, right? And this is high school maths, right? So you just take the derivative and see the first order condition, and then you check the concavity or convexity of the function, and you have the maximal point when C is equal to A. Okay, that's it. So now things are probably more well organized from now on. So we're going to consider a binary classifier again, right? Where the confidence value, sorry, before that, f of x is giving you the probability of for class A, okay? And the probability for class B is automatically taken as 1 minus f of x, okay? And class A is predicted when f of x is greater than 1 over 2, and vice versa. And let's say your confidence measure for your prediction is actually taken by the max value between f of x and 1 minus f of x. So if your prediction is class A, then your confidence value is f of x. When your prediction is class B, then your confidence value is 1 minus f of x. I think this is clearer than the previous case, right? And now the C of x, which is defined as the max probability between these two choices, we wish to show that this actually estimates the probability of prediction being correct. Okay. Where y is the probability of prediction being correct. Okay. So so what are the cases where the prediction is correct? Either the model predicts class A. Sorry, yeah. I equals 1. You see, I was confused as well when I was writing this slide. Yeah, the probability of prediction being correct is just when y is 1. Yeah. And log probability proper scoring, what log probability proper scoring says is that when the prediction is correct, the reward of log of cx should be given, okay? And when the prediction is incorrect, then I'm going to give the reward of log of 1 minus c of x, okay? That's what the proper scoring rule says, right? For log probability. And we have 4 different cases here. Yeah. So I should really introduce a different variable than y here for the ground truth. Let's, yeah, for now say it's z, right? Z for the ground truth. So these were A and B's, right? In the previous slide. So when the actual class is A and the prediction was negative, it's class B, right? Then, oh my God, yeah, it has to be B and A actually. Yeah. I promise to, yeah, sort this out. So when the actual class is B and the prediction is B as well, then the reward is C of x, okay? And if you actually plug in the definition of C of x, it turns out to be 1 minus f of x for the prediction of B, okay? If you remember this here, okay? And when the actual class is A and the prediction is B, then this is wrong prediction, and therefore you should give the reward of 1 minus c of x. And actually that turns out to be f of x for the prediction of B. And if you do the computation for all 4 different cases, then you're going to get the reward of log of 1 minus f of x for the case where the actual class is B, and log of f of x for the case where the actual class is A. Okay. And that corresponds to the loss function where so yeah, this should be z equals to B again here, right? So when z equals to B, then the reward will be log of f of x, right? Which corresponds to, in this case, oh yeah, y should be A, right? Z is A. And when z is B, then you get the reward of log of 1 minus f of x. And this corresponds exactly to the log likelihood loss for the binary classification task. And this is called binary cross entropy loss. And this is the loss function that we are using all the time for training deep neural networks, right? So what this shows is that this loss function is actually not only doing the right job for making the model predict the right class, but also making sure that the confidence value, which is defined as the max between these 2 values, to be truthful to its own prediction confidence. The probability that your prediction is going to be right, actually. So BC is really good. Now let's take a look at the multi-class cross entropy case. I'm pretty sure from this point, the notations will be in order. So now f of x is not a single number, but a vector actually, with k different classes. And now what I'm going to define as the confidence measure is the max probability among those predictions. Well, actually, the f of x should be probability that should sum up to 1 here. So it's not only in real numbers, but also between 0 and 1 range, and they should sum to 1. Okay, and we define the proper scoring rule for this confidence value to be log probability again. And then we have the criteria for the proper scoring rule for C of x as follows. So it's log of C of x for correct prediction and log of 1 minus C of x for wrong prediction, right? And I just plugged in max over fk in this formulation. So we can we have the same formulation here, and we can actually simplify this into this one here below. So when y is equal to argmax f of k, then the max k over fk is exactly fy, right? Because the max is taken at k equals to y. So I can simplify like this. For the second case, remember that fk are probability values. And so taking 1 minus max of them means that you're summing over all the non-maximal values of fk, right? And the max value is not taken at y either. And therefore, you can split the sum here into the summation of f of y of x plus every term in fk, where k is not y and k is not argmax. It's the same thing, right? I hope it's clear. Yeah, because if you sum fy and then this whole summation, then you have summation of fk except for y itself, except for the argmax value, and that's exactly 1 minus max k. Okay. And now we have this formulation, and we note that this can be bounded from below. Okay, so because in the first case, this is exactly log of fy, but in the second case, this is greater than or equal to log of fy of x. Yes.
So in this case, y is the ground truth.
Yeah, y is the ground truth in this case. Yes, and the correctness of the prediction is dictated by y being equal to argmax fk. Yes. So the proper scoring rule can be bounded from below, and if the goal is to maximize the proper scoring rule, then we can also try to maximize the lower bound of that objective. Okay, so in other words, we can try to maximize log of fy, and that's exactly trying to minimize minus log, negative log likelihood, basically. Okay, and negative log likelihood is exactly cross entropy loss. So again, here by trying to optimize the cross entropy loss, we are also encouraging the correct confidence prediction, where the confident value is defined as the max probability over the prediction of values. Okay. So we learned something here, right? We can keep using cross entropy as before. That's going to give you a fairly nice classifier, but also that's very likely to give you a good, well calibrated or well kind of adjusted confidence values based on max probability. Yeah, but also having a good objective does not essentially mean that if you train with that objective, you're going to get a nice solution. Because during the optimization procedure, a lot of things can just go wrong, and the model may overfit or anything, right? And then the model then probably fails to represent uncertainty anymore. Okay, so that could happen. So in machine learning, you always need to empirically check if things are working. Yes.
But even if we overfit, we want, so the model can optimally tell us how certain it is in its prediction, and it will still work out. It's just that it's too confident in its wrong prediction, right? So CX, so the theory still holds. It's just that it's useless because it's confidently wrong.
Yeah, but there are two layers of it. So the other layer is the generalization gap. The objective is right, but it does not guarantee that the objective turns up. The objective is also observed outside of the training samples. Right? I mean, that is happening for any machine learning, right? You're fitting some function, and yeah, the function fitting is not guaranteed outside of the training samples. What is actually very interesting here is that usually on the training set, yeah, so the first thing is on the training set, it's very likely that your confidence estimates will be correct because you're training with a proper scoring rule. But actually for the training samples, the confidence values do not matter anymore because you're anyways going to get 100% accuracy. And there's no point in measuring confidence anymore. So in training samples, everything is very easy. But as soon as you go outside of training samples, things break, and the way things break kind of compounds on top of each other. And yeah, again, we need to check everything empirically, therefore. Yeah. So how do we check empirically for test samples? It turns out that cross entropy is also a nice evaluation measure, of course, because it's a proper scoring rule. Here again, we can use cross entropy for multi-class classification task over the test samples, right? So we're going to take the average of the cross entropies over all the test samples. And here, lower is better. And this is an example of how people measure the degree of correctness of the confidence prediction. They measure the negative look likelihood over the test samples, and lower is better here. So the rows here are different data sets, so you have to always compare horizontally. And these are different methods. And you see that in certain cases, you see that some of the methods, usually the deep ensemble, it seems they are giving better results than the others. That's how you read a table like this. In natural language processing context, people use terminologies like perplexity especially for language models like GPT-3 and so on. They also use perplexity for some benchmarks. And perplexity is just exponentiated value of negative log likelihood. Well, there's caveat of having to take log base 2 here, but essentially they are showing the same information as before, as negative log likelihood. Some people also use other scoring rules like Breyer score. And this is the form for multi-class Breyer score. And yeah, strictly speaking, again, this representation of Breyer score provides an upper bound on the Breyer score for the max probability confidence estimate. So it's not the exact proper scoring rule, but still it's an upper bound, and therefore trying to minimize that will guarantee that we are getting better calibrated, better represented confidence values. And as a small exercise, you may wish to kind of prove why this is only providing an upper bound on the actual Brier score. Okay. Calibration evaluation. So we use proper scoring rule and calibration in different terminologies, but to me, essentially, they are showing the same thing. So what is the definition of calibration? It's another terminology referring to the estimation of confidence, such that confidence level actually reflects the true predictive uncertainty, the actual probability of getting the answer correctly. And typically people show these kind of plots where the x-axis is the confidence level and the y-axis is accuracy. So you're basically binning through all different confidence values here and checking the accuracy in different confidence bins throughout your test set. And of course, for the confidence level of between 0% and 10%, you expect the actual accuracy for this bin to be close to 5% or somewhere between 0% and 10%, okay? And so on. And that is an example of a well-calibrated model. And if things are not well-calibrated, then probably the bin index and the actual accuracy for that bin do not match that well. So precisely how do you evaluate calibration algorithmically? We let the input be X and Y output be Y, okay? But here again, it's multi-class classification task again. And we get two different outputs from the model in this case. One is the prediction of the class, and the other one is the prediction of uncertainty. Doesn't necessarily have to be max probability here, okay? And then we define what we mean by perfect calibration as the conditional probability of correct prediction given the confidence level, P. For this confidence level, the probability of correct prediction should be exactly P. And that should hold for all values of P. That's what we mean by calibration. And that's actually very similar to what we meant by predictive uncertainty, the correct prediction of predictive uncertainty. What does that imply, for example? I'm just giving you an example here. So when we consider, let's say, P equals to 0.8, then we collect all the samples in the test data set where the confidence value was 0.8, and we compute the accuracy across all these samples, and they should be correct 80% of the time, roughly. Okay, and this is the exact algorithm where you compute the something so-called expected calibration error, which is basically measuring the deviation for your confidence prediction from the perfect calibration. So first you train some model, and then you generate the predictions to tell whether your prediction was correct or wrong. And then you have confidence estimates estimated from your model as well. And then based on the confidence estimates, we can put the test data into M different bins, depending on the level. So we typically use large M equals to 10, so 10 different ranges. And for example, this bin contains all the samples with prediction confidence between 60% to 70%. And then for each bin, we are computing the accuracy, which is the proportion of correct predictions, and the average confidence value. Well, this is going to be some value between, let's say, 60% and 70% in this case, but we still usually take the average to make sure that we are more precisely following the actual confidence values in this range, okay? And then the expected calibration error is you basically take the difference between the accuracy value for this bin minus the confidence, average confidence in this bin. And then this value, the difference here, should be as low as possible for perfect calibration for every bean. So we measure the absolute difference here and then average them across different beans. So usually it's just 1 over large M, but in case when you have different number of samples in each bean, which is actually usually the case, actually, yeah. And you have different weighting, okay, for different beans based on the population. So again, perfect calibration is when these two match. And we can measure the deviation by taking the difference, absolute difference, and taking the expectation over different p-values here. And yeah, expected calibration error is just a finite approximation of this value here. You can also measure maximum calibration error, which is taking the max difference between the accuracy and the average confidence value for different beans. Yeah. One critical, okay, first the advantage of using ECE compared to proper scoring rule, it's going to give you some number that is between 0 and 1, which is telling you how much you are deviating from the x equals to y line, right? So this is very intuitive and nice. And this is kind of different from, let's say, this kind of table where you see some numbers which are sometimes positive, sometimes very large, sometimes -5. And I can't tell, what does that exactly mean? Does that mean it's good or it's bad, right? But ECEs tend to give you a good indication of, yeah, whether this is fairly well calibrated or not. But the drawback here is that ECE is not a proper scoring rule. Okay, what does that mean? ECE can be minimized even for non-true or false predictive uncertainties. You can arbitrarily make some confidence values for every sample in your test set, and then that could be kind of designed to give you expected calibration error to be 0. And so if someone is really determined to game the metric and win the competition in the benchmark, then they can always do this using the ECE metric. So exercise 3 has a good question on for you to kind of devise this kind of trick. The other drawback is that ECE metric depends on the binning as well. Let's say you use just 1 bin for everything, right? Then it's going to give you a very different score. And so there should be some kind of agreed upon number of beans for comparing this. But also, like, fixing the number of beans is probably not a good idea in the long run, because eventually the models will be making correct predictions more and more, and therefore you should probably be more fine-grained near the 90 to 95% confidence range, because there would be probably a lot more samples there. So yeah, it's kind of not clear. So there are pros and cons. And this diagram that I have shown before is called reliability diagram. And ECE measure is kind of visualized here. So the sum of the differences everywhere, the weighted sum of them is called expected calibration error. If you just look at the max, this red region among all the beans, then that's called MCE. Okay. So we have looked into proper scoring rule and calibration metrics so far. And yeah, I'm going to tell you a few more metrics. Before that, we take a quick look at how well calibrated current DNNs are. So this is a paper from ICML 2017, and they looked at rather old network, LINET, and more recent ResNet. ResNet is also archaic by now, but it was like that by then. And they say the recent models tend to be less well calibrated compared to old ones. And they try to tell us why that is the case. And they look at the response of ECE with respect to different factors like increasing depth or increasing the width of the model. And it turns out that if you increase the depth, then the calibration gets worse. And if you increase the width, the calibration also tends to get worse. They don't tell us why they think this is happening, but they're just reporting this is the case. Yeah. And they also show that the negative look, like the test NLL, which is also another calibration measure, right? It tends to increase after some epochs for some training, meaning that yeah, test error is also kind of showing some kind of a little bit of overfitting, right? It's increasing after some epochs, but also the test NLL is even more overfitting to the training samples. Okay, so this is another type of overfitting, another level of overfitting. The C of X also overfits. And they introduce an easy fix for making ECE measures better. This is called temperature scaling. A lot of models use softmax at the end of the layer to make the values be in the range of 0 and 1, and they sum to 1, right? But of course, you can introduce some temperature here. Temperature is a positive scalar that is divided throughout the logit values. And when T is approaching 0, the softmax values will approach to a one-hot vector. You're stressing the argmax value more, but if you increase the temperature, then the output becomes more uniform. Okay, because everything is approaching to 0 in this case, right? So one fix you can make is that you can make sure that the predicted confidence to be so this is your yeah, so if you're using a max probability of as your confidence value, then you wish your max probability values to be following a good calibration. And so yeah, you can alter T on your validation set and try to look for a T that is going to give you the best expected calibration. I think you can do just grease search over different T values and find the one that's best. And here's the results of your ECE values after you do the search over the validation set. So if you're just using temperature 1, then you're going to get not so great calibration results, right? But of course, by just scaling temperature, you're going to get very good results, all smaller than, let's say, 2% in general. Okay, so that's an easy fix. And actually, if you look at more recent papers from NeurIPS 2021, they revert the previous observation from ICML 2017, saying that more recent VIT and mixer variants are actually well calibrated. And you see, yeah, the reliability diagrams show good calibrations in general. And EC values tend to be smaller. This Gu et al. Is the ICML 2017 paper, and they reported values here. But now with all these recent variants, we have very low calibration error. That's what they are saying. Okay, so yeah.
But it also would because that much more data.
Could be, yeah. I haven't checked if they all use the same number of training data, but yeah, maybe the deciding factor is the number of training data, because yeah, it looks like it has to do with overfitting as well, right? So if that is the case, then increasing the training data could be a good solution. Yeah. But the final question is, do we actually need calibration at all? Because we can think of a weaker condition than calibration, which is saying if the true probability says one sample, x1, is more likely to be predicted correctly than x2, then instead of saying the C should be exactly predicting the actual probability, we just require that the ranking should be preserved. The confidence values are kind of in the right order, right, of the true probability. If this ranking condition holds, then we can also think of a monotonic post-processing calibration function, which is 1D function. That can be applied on top of the confidence values to put them into the actual probability values. There exists such a monotonic function, right? So once you have the correct ranking, all you have to do is to find the monotonic function that puts everything in order. And therefore, probably instead of requiring that the huge deep neural network to eventually be printing out the right calibrated confidence values, probably it's more realistic to just say they rank the samples in the right order, okay? So based on this intuition, people have produced different metrics for quantifying the ranking condition. So you're going to have two ingredients again. So the CIs are the confidence values for sample xi, and you're going to have the correctness of prediction Li throughout your test data, which is telling you whether your prediction is correct or wrong. Okay. Yeah, I should use Li for the previous slides probably. So instead of exactly as trying to estimate the predictive uncertainty, PI, we can only use the binary values Li, because in ECE, expected calibration error, what we did was to bin the Li values and then took the average. And that's going to give us some averaged accuracy over the bin. But in this case, we don't do that. We just use the raw 0-1 values of correctness and incorrectness and try to see how well the confidence estimates are a good estimate of Li values. And in other words, this is now a binary detection task based on CI. Can CI tell us anything about the prediction correctness? Okay. And of course, for detection metrics, I think many of you will be familiar with this, but reiterating, you can measure, for example, area under curve, AU-ROC, ROC curve, and precision recall curves, right? To summarize, true positive at threshold T is exactly when you have the true positive sample, and also the confidence value was greater than T, meaning that your prediction was also positive. So this is truly positive ones. And false positive means your prediction is positive, but actually the ground truth was negative. True negative means the ground truth is negative and your prediction was also negative. False negative means your ground truth was actually positive, but you falsely say it's a negative sample. And, oh, you should take this set sizes everywhere. But yeah. So precision here means the number of training true positives divided by the full number of positive predictions. Okay, so how pure is your positive prediction at threshold T? And recall means how many of your actual positive samples in the data set are recalled at threshold T. And you can, of course, draw precision recall curve by varying T from -infinity to +infinity. And then you can measure the area under curve for this precision recall curve. And that's going to give you a good estimate of how well you're detecting, how purely you're detecting your correct predictions based on CI values. So area under precision recall will be 100% for a perfect detector, like here, which means you're recalling once the first sample, and the first sample is true positive. And the second sample is also true positive. all the way through your recall of every sample in your positive set. All your positive samples are, while you are recalling all the positive samples, your predictions have been always positive as well. Okay, and that's exactly when your AUPR is 100%. But actually, even for random detector, you're going to get AUPR equal to the ratio of positive samples. Because if you're making prediction for your correctness at random, right, then your precision will always be very close to the actual proportion of positive samples. And the problem is that when this is a highly imbalanced test set, where the positive class is 99%, then your baseline AUPR is already 99%. And therefore, you don't have a good resolution of how much improvement you're making on top of the random classifier, random detector. Okay, yes?
Is the area under the curve the same as average precision? So the definition of average precision?
Yes. Yeah. Mm-hmm. Yeah, you can use average precision as well. Yeah. It's the same thing. Yeah. And so what people also take a look at is AU-ROC, where AU-ROC is the area under ROC curve. And what is ROC curve? All right, I have explanation here, right? So it's the curve between true positive rate and false positive rate. True positive rate is exactly the same thing as recall. False positive rate is something similar to recall, but this is the recall for the negative samples, okay? So among the negative samples, how many of them are wrongly predicted as the positive sample, okay? And the nice property of AU-ROC is that for random classifier, you're gonna get 0.5%, sorry, 0.5 always, regardless of how many of the samples in your test set is positive. Okay, so for imbalanced data set, AU-ROC is recommended. And yeah, the AUPR and AU-ROC or AUC, it's also called AUC, and they are better confidence values will be represented by higher values of those area under curve, and you can benchmark progress using those estimates. So I have a few more slides here, but probably I'm going to defer them to next lecture and stop here. Thank you.